We're going to explore this question right here about the feasibility of being able to solve any quadratic equation. So by it being an equation, of course, it means it has an equal sign, but then also the nature of it being quadratic means that the highest exponent on the variable term is just going to be a 2 in the equation. So like what we really mean by this is like we could have something just absolutely crazy, like just kind of making this up. 1,296x squared minus 354.93x, and suppose that was equal to negative 3/2 x squared plus 4x minus 17.5, right? So just lots of interesting stuff going on, right? Would it be possible for us to solve that equation, right? Is there a kind of nice way to be able to do so? So with this equation and with any other quadratic equation, one thing that we would always be able to do is somehow kind of cancel out terms on one side of the equation so that we collect all of our terms onto the other side of the equation and therefore then get a 0 on one side of the equation. So no matter what those numbers are, then we could always get a quadratic expression. So in other words, have a highest x squared term that's multiplied by some number that I'll just call a, and then you'd have your x term, so some number b, let's say, that would times with the x term, and then just some other number that I'll call c, right? And then you'd have your 0 on the other side, right? So we could always get a quadratic equation in this form if you just got everything on one side, right? So this applies for all quadratics, right? Okay, so I'm going to try to solve this, and I'm going to try to solve this by completing the square. And so we know that with completing the square, what we could do is we could leave the x squared term and the x term as they are, and then I'm going to go ahead and subtract this number c to both sides, which means that I would get negative c on the other side. So in order to complete the square, though, it's easiest if the number right there in front of the x squared is a 1. So to make it a 1, I'm going to have to do the same thing to both sides of the equation right here by dividing by an a to successfully accomplish our goal then of getting just 1x squared. And then we would actually get b over a x. And then that's going to be equal to the number negative c over a. So now that we have just a 1 in front of the x squared right there, now we can complete the square. So we know that with completing the square, we want to use that number, that's the coefficient of x. And what we want to do is we want to first of all take half of it, right? So for example, if it was like the number 6, then we would take a 3 and then square it, right? So we don't know it's a 6 though, we just know that it's b over a. So half of b over a would be b over 2a. And then I want to take that and square that, and the result of that then will give me the thing that needs to complete the square right here. So if I figured that out, if I squared b squared over 2a, it would be b times b on top, and then 2a times 2a on bottom, which gives you 4a squared. And then we would have to add the same thing to the other side to keep this equation balanced. So we would add b squared over 4a squared. All right, so what we've now accomplished is now this expression that's on the left-hand side is a perfect square trinomial. And we're going to be able to factor that as x plus b over 2a, since that was half of that coefficient of x there, times x plus b over 2a. So in other words, x plus b over 2a squared. Now, on the other side, this and this really are just kind of numbers because they just involve a, b, and c, which we're just assuming are numbers. So they're trying to be added. And so in order to add those things together or to add fractions together, you need a common denominator. And our denominators are not common. One of them has an a and the other one has a 4a squared. So what I could do is I could multiply that first fraction that we have right there by a to get a squared, but also by 4. So I'm going to have to multiply by 4a over 4a. So really what I'll get then is I will get 4a squared, and then I can add the fractions together. So add the tops together. So one of them has a positive b squared, and the other has a 4 times a times c, but be negative. So I can just write it as b squared minus 4ac like that. So now that we've completed the square, we can actually just then solve by square root property to kind of finish this off. So if you square root that, you're going to end up with then the quantity of x plus b over 2a, and then that's going to be equal to the square root of that side. Now that's really a fraction, and we know that we can write it as a separate square root of the numerator over a separate square root of the denominator, and that's going to help us simplify this. So I'm going to write this as the square root of b squared minus 4ac, and then that's going to be all over the square root of 4a squared. So because this was also just a number, because it involved A's, B's, and C's, we actually get both the positive and the negative roots there as well. So it does turn out that actually right there, the square root of 4a squared we can simplify because 2a times 2a equals 4a squared. So I'm going to be able to write that as plus or minus the square root of b squared minus 4ac. I'll just leave that as it is over 2a. And then I'm also going to get the x alone by subtracting the b over 2a. So I end up getting that x is equal to negative of b over 2a if I subtract that to both sides. And then you'll notice that then this fraction and this fraction actually do have common denominators, and they're being added. They have the common denominators of the 2a. So I could kind of finally finish this off, write it over here, that x would be equal to all of that over 2a. So it's going to be negative b plus or minus the square root of b squared minus 4ac. And what we've done right there is we've now actually solved for the value of x, right? Given any a, b, and c values, right? When we got all of the terms to one side, as we did over here, right, and set it equal to 0. So it just turns out that the solution to any quadratic equation is based on this. And this is what we call the quadratic formula. You just saw derived the quadratic formula in terms of where it comes from, so I want to just formalize that a little bit here, that for any quadratic equation, right, so where you've got a bunch of x squared terms and x terms and constants, right, you're able to always collect those terms onto one side and therefore have a 0 on the other side, and that's what we did to derive the quadratic formula. So whenever you have a quadratic equation where there's a 0 on one side of it, and then you just combine all your x squareds together, and so you'll just have some number a times with x squared, and then you add that to your x term multiplied by some constant number b, and then just a constant only, right, just a number c. If you get an equation of that form, and so those a, b, and c values are just any real numbers, so they are real numbers, then we can actually take this equation and figure out what the x values can possibly be by using the quadratic formula. So based on that, then x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that gives us the quadratic formula. So we just have to note that a cannot be equal to 0. The reason why that is because if a were equal to 0, then you actually would have a 0 in front of your x squared, which means it's not going to be quadratic in nature. It would kind of reduce it down to just bx plus c, so something that might be like linear in nature, right? So that would also be a problem because if a was 0, you'd have an a on the bottom, so you'd end up dividing by 0, which is undefined, right? So it makes sense that a cannot be equal to 0. So realize that the quadratic formula can only be used on equations that are quadratic. So like if you had an equation where x had a power that was higher, so like if you had x cubed minus 2x is equal to 4x squared plus 8 or something like that, and you're trying to solve, that is not a quadratic equation because there's an exponent that's higher, right? So just realize that the quadratic formula can only be used on equations where, yeah, like the highest exponent on x, right, is going to be a 2. So we're just going to look at examples where we can solve these equations by using the quadratic formula. So this is an equation where x squared minus 10 is equal to 3x. So in order to use the quadratic formula, though, you really want to get a 0 on one side of the equation. So I'm going to start by subtracting 3x to both sides to accomplish that goal, because then I get a 0 on the right-hand side. And then I'll have x squared minus 3x minus 10 on the left-hand side. So you need to realize what exactly are your a, b, and c values. So I do have a 1 right in front of the x squared right there, so that's going to be my a value. And then my b value is a negative 3, so you want to include those subtractions if there's a subtraction in front of it. So it's a negative 3 for your b value. And then we also have a negative c value right there, so my c value is negative 10. So I'll write the quadratic formula one more time generally, but then from this point forward, I'll just kind of plug into it. So we know that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So now that I've just written it generally, I'm going to now plug in the actual numbers that we have. So I want to take negative of b. So this is where I'm going to have to plug in negative 3, since that's my b value, and then plus or minus the square root of squaring b. So again, I'm going to have to plug in negative 3, because that's my b value, and then minus 4 times a times c. So there I'm going to plug in the 1 for the a, and then plug in the negative 10 for the c, and that's going to be all over 2 times the a value, which is 1. All right, so then it's just kind of a matter of like simplifying all of this from here. So what you'll notice right there is that you do have negative of negative 3, which will give you a positive 3. And then inside of the square root, you're always going to want to times like those 3 numbers there in a row. So you'll notice that you do have a negative and a positive and a negative all times in. So when you times a negative with a positive with a negative, it's going to end up being positive. So we will end up with then plussing of 4 times 1 times 10. 4 times 1 times 10 is 40. This right here will always be positive, okay, because you're always squaring it. So that's just going to be a 9. And then that's going to be all over 2. So it turns out then that we end up getting 3 plus or minus the square root of 49 on top, right? And we actually know the square root of 49 is 7, so I'm just going to erase that and write that as 7, and that's all over 2. So you can actually find really nice numbers for this particular equation, because if you did the plus, then positive 3 plus 7 gives you 10, which then over 2 gives you 5 as an answer. And then if you did the minus, then 3 minus 7 on top gives you negative 4, which divided by 2 gives you negative 2 as an answer. So it turns out then that that's the values for x, and so we said x equals that. So I will be able to conclude from this then that x equals either 5 or negative 2 are going to be the solutions for that equation. Okay? Now, I want you to recognize that there are other ways that you could solve quadratic equations sometimes that might be faster than quadratic formula, and this would be a great example of that, because if basically once we got all the terms on one side, this was kind of the original problem, because we got such nice answers, then it's going to actually factor nicely over the integers, because you could actually factor x squared minus 3x minus 10 as x minus 5, so you have a little bit more negative, and x plus 2, because then it FOILs out to have the negative 3x and the negative 10 in there, right? And therefore, then you get that positive 5 and negative 2 would be the solutions, and those are the exact things that we got just via the quadratic formula, okay? All right, so like I said, I'm not going to copy the negative b, that sort of thing. I'm just going to kind of plug directly into the formula as we go through some more examples here. So as we can see here, we've got an equation where we've got some different expressions on both sides. Ultimately, it's quadratic in nature because you just have some w squareds and w and constants. We do know that we need to get all our terms on one side. So why don't I subtract the 4w squared, and then it'll combine with that one since those are like terms. So we're going to get 3w squared there, and that'll cancel out. And then I'm going to also need to then, I guess, cancel out the 30, so I get a 0 on that side. So when I subtract 30 there, there is no other like term with that, so you'll still have the plus 13w and then the minus 30. So treat each of these values, your 3 and positive 13 and negative 30, as your a values, as your b values, and your c values, right? So the only negative value we have to work with right there is your c value of negative 30. So the quadratic formula says that the values for w in this equation, because that's the variable we're solving for, is going to be equal to negative b, so negative of 13, plus or minus the square root of your b squared, so 13 squared, minus 4ac. So the a is 3 and c is negative 30, right? That's the only negative one we have in this one. And that's going to be all over your 2 times your a, so 2 times 3. All right, so simplifying this all out, we're going to get negative 13 plus or minus the square root. So if I start with the 13 squared, that's always positive, it ends up being 169. And then right there that I just underlined, we're going to times those 3 numbers together. It's a negative and then a positive and a negative. So we're end up with a positive. 4 times 3 is 12, and then 12 times 30 is 360. So we'll end up with that. And then finally, over 2 times 3, which gives us 6. So moving forward from there, we still have negative 13 plus or minus. So if I add together the 169 and the 360, you're going to end up getting then 529. So it does turn out that actually 529 is a perfect square because it is actually 23 times 23. So you end up getting negative 13 plus or minus 23 over 6. So then we can kind of find the two individual things we're going to get here. If we plus first, I would do negative 13 plus 23. That would give you 10 positive over 6. And then if I minus second, negative 13 minus 23 is negative 36, which is over 6. So both the red and the blue fractions that I wrote there are the two solutions, but you're able to reduce them, so just make sure that we reduce them. So the red one that we got for W was 10/6, which reduces down to 5/3. And then the blue one, actually, it's divisible by 6, negative 6 times, right? So those values right there of 5/3 and negative 6 are the values for W that satisfy that equation. All right, and then jumping down to this fella right here, let's go ahead and collect everything on the left-hand side. How about? That's kind of how I've done it for the other examples. So I'm going to go ahead and add n squared to cancel out negative 1n squared, and then add 1n squared there, which will combine with that since those are like terms. So we'll end up with 9n squared then. I do need to kind of unlock that and distribute that negative 2, right? So we actually have negative 6n and positive 2, because it's negative 2 times negative 1. So then to actually cancel it out, I really actually need to add 6n to cancel out the negative 6n. So I'll add 6n, which will make it positive 4n there. And then finally, if I did subtracting of 2 to cancel the positive 2, I'd subtract 2 there. And negative 14 minus 2 is going to give us negative 16. All right, so again, then keep in mind that the number in front of the squared variable is your a value. That's going to be your b value, and then the constant term is your c value. So using the quadratic formula, now we're solving for n. So n is going to be equal to negative of b, so negative of positive 4, plus or minus the square root of b squared minus 4ac. So I'll plug in the 9 for the a and the negative 16 for the c, all over 2a, so 2 times 9. Then just simplifying this a little bit right here. If I do the 4 squared inside that square root, we get 16. And we have a negative, positive, negative times in, so that will be a positive. 4 times 9 is going to give us 36. And 36 times 16 is going to give us 576. And then that's going to be all over 2 times 9, which is 18. So with this one, now we get negative 4 plus or minus the square root of 592. So it turns out that now this is kind of the first time in the examples we've seen so far that the number under the root, which we call the radicand, so 592 is not a perfect square. So we're going to have to simplify it by maybe trying to find, a perfect square that goes into 592. So with 592, it does turn out that it is divisible by 16, and that would be the largest perfect square. So if you put this into a calculator, and if you want to check this on your own, you certainly can. 16 and 37 are the two numbers that can times to equal 592, and then 37 is prime. So we know then that 16 is going to be the largest perfect square. So if I can rewrite the square root of 592 as that, then I know that that's actually just going to simplify down to 4 root 37. So now with this sort of a style of things here, what I'm going to need to do is you actually need to kind of write this as two separate fractions at this point. So what I mean by that is you want to write this as negative 4/18, and then plus or minus, and then because it's simplified down to 4 root 37, we want to reduce that down to 4 root 37 over 18. So we kind of get this part that doesn't have any roots and then we'll have this separate part over here that has roots. It does turn out that you can simplify the 4/18, and that's also 4/18 because it's 2/9. So you'll end up getting then negative 2/9 plus or minus 2 root 37 over 9. And that right there gives you the solutions for W. So why don't, or for N in this one. So I'll put N equals for that. So that gets the solution solved for there in terms of exact solutions right there. So it's really important that you understand that we will be able to get decimal answers for this as well. So I don't really have a calculator that I can pull up nicely right here, but in terms of finding them, you're going to get two possible answers. So what you would need to type into a calculator is you need to type in negative 2/9, actually for both of them, right? But one of the times you would plus 2 square root 37 over 9, and the other one you would subtract 2 root 37 over 9, and you put it in a calculator. Now, of course, like the decimals are going to be crazy. It's going to go on forever. So, round it to a few places or so, just to give a little bit of somewhat accuracy to that. But yeah, that would be what you would type in if you need to get kind of just an approximate number for what N could be. There's just a couple examples here that I want to show that illustrate how we get some complex solutions to quadratic equations through using the quadratic formula. So when we get complex answers anytime, right? Whenever you have complex numbers, you always want to make sure that you always write it in the standard form of a complex number in a plus bi form, so that you always have a separate real number plus or minus with the imaginary part of the number. Okay? All right, so right here, we're asked to find the zeros of the function. So in other words, we want to find the b values that can plug into this expression that's going to make the output h of b equal to 0, right? So we really want to get an answer of 0 by plugging in some number b, right? So it actually just turns out then that this expression right there is a quadratic expression, and it's ready to go in terms of using the quadratic formula, right? We just realized that, okay, that number is our a value, and then negative 2 right there is the b value. Don't get that too confused with the b variable, right? And then, the c value is positive 5. All right, so as we know with the quadratic formula, we're solving for the variable b, right? So b is going to be equal to negative of b, which is negative of negative 2, since your b value is negative 2, plus or minus the square root of b squared minus 4ac. And that's going to be all over 2 times the a value. All right, so with that then, just doing the simplifying here, that part right there is negative of negative 2, which will give you a positive 2, plus or minus the square root of negative 2 squared gives us 4. And then you'll notice right there, negative 4 times 2 times 5 is going to give us a negative, because there's only one negative times in there, and it would be 40, so minus 40. And that's going to be all over 2 times 2, which is 4. All right, so what we end up here getting then is 2 plus or minus the square root of negative 36 is 4 minus 40, and that's going to be all over 4. So it turns out that the square root of 36 we actually know is 6, right? But since it has a negative, it's actually 6i. So we end up getting 2 plus or minus 6i, and that's all over 4. So we don't want to leave it like that. We want to write this as a separate real number plus or minus with an imaginary part. So I want to write that as the 2 fourths and then plus or minus the 6i fourths, or just 6 fourths and with I after it. And then it just turns out that we can actually reduce the 2 fourths down to 1/2 and then the 6 fourths down to 3/2. So there we go. It turns out then that the b values that satisfy that equation, or that are the zeros of the function, are 1/2 plus 3/2 i, or 1/2 minus 3/2 i. Excellent. All right, just one last example here that we'll cruise through, and then we should be pretty solid and golden with quadratic formula. So this example right here, let's solve it. It's a quadratic equation. Let's get a 0 on the right side. How about? So let's subtract p. There aren't any like terms, so it'll just be 10p squared. I'm going to sneak the p right in there in the middle. So we have that b value there, and then plus 9, and that's going to be equal to 0. All right, so just recognize that your a is equal to 10, and your b is going to be a negative 1, because it's negative 1p, and then your c value is a 9. All right, so solving for p then in this equation, it's going to be negative of b, so negative of negative 1, plus or minus the square root of your b squared minus 4ac, and that's going to be all over 2a. All right, so with that, then if I do negative of negative 1, we get positive 1 plus or minus the square root of 1, and then minus 4 times 10 times 9, which is, there's only one negative, so it's going to end up subtracting. 4 times 10 is 40. So yeah, it's going to be 360 subtracted from the 1, all over 20, because that's 2 times 10. All right, beautiful. So then with this, I'm just going to split this up as separate fractions right now. How about? So let's write this as 1/20th, and then plus or minus whatever we get there on top over 20. So 1 minus 359 gives you negative 359. So we can't leave negatives inside of roots, right? So we want to simplify that, and since it's inside of a square root, it's actually imaginary. So I'm just going to go ahead and erase that negative and then throw an I in front of that. It does turn out that actually 359 does not have any perfect square factors in it, so we're not able to simplify square root of 359 any further. It's already a radical that's in simplest radical form. So yeah, we can't reduce like 1/20th, and that's 1/20th as well. We can't reduce it. So yeah, we're pretty much done. So that right there gives you the two complex solutions for p, for that quadratic equation.